All right, we left off. We just got the general form of this, right? Now the goal is to find the functions. R of 0. And tell us what that has to be, right? Based on what we have, we have that, and that's equal 4, 1, 1. But if you just look at it, you should be able to see that F0 has to be 0. Take F of t to be some constant times t. This will allow us to now find R of 8, or use R of 8 to find K. If you subtract 4, 1, 1 from both sides, what are you going to get? That's going to be 5, negative 4, 2, isn't it? 8K would have to be 1. K would have to be an 8. That would be a vector parameterization. Not the only one that would satisfy these two conditions, but probably the simplest one. Again, theoretically, you can use any function, f of t, where f of 0 is 0, and f of 8 is 1. having the same argument. We just have different conditions. That has to equal P, which if you write it out as a vector, 411. So I'm sorry, that should not be f of 0, it should be f of 6. F of 6 has to be 0. Oh, I did forget domain here. T is any real number. That's f of t. Take f of t to be some constant times t minus x. Again, f of 6 has to be 0. Could also use 6 minus t. R of 10, we're going to get 4k, right? And that has to equal q. Again, it should be difficult to see that 4k is going to wind up being 1. Means k has to be a quarter. And that would then be your f of t.
How is the f of 10 4k for bottom part?
10 minus 6. I'm plugging into what I said f of t was.
Oh,
And again, it's not the only one, right?
wait, and why did you say that ft is that?
Because f of 6 had to be 0.
Oh,
Right? Specifically, once again, f of 6 has to be 0, f of 10 has to be 1. Any functions of t that satisfy those two conditions would work. This is just the easiest way. Exact same set of questions worded differently, we have two different values, right? We have r of 0 and r of -2. without doing any work, that's the same as part A. So just take kt as your function. Again, k is a constant. With that second condition, we find that negative 2k has to be 1, right? Or f of negative 2 has to be 1. Which makes k negative 1 half. That would be the parameterization of those conditions. Right. All three parameterize the exact same line, just with different parameters to represent your initial and terminal point. Right? Initial point's P and terminal point PQ. And if you're just asked for a parameterization with no conditions, just set f of t to be t and you're done. So again, fairly straightforward, nothing really different there. Being able to parameterize curves is going to be really important when we study line integrals later. X equals negative 5z squared. And it says it's in strictly the xz plane. Well, if it's in the xz plane, y has to be 0, right? Well, that's kind of already in a parameterized form, isn't it? Second parameter would be z. That'd be a parameterization. So we are missing a domain. And z can just be anything. No, it's because of the curve. X equals negative 5z squared. There's no restriction on that domain, right? Which allows you to be anything you want. Yeah, okay, so those I actually added in, so I don't have notes on the next questions, but that's okay. That shouldn't be too difficult to do. Just limits of vector value functions. Now remember, when we're taking the limit from vector value functions, the limit of each individual component. So you can distribute the limit through. Again, distribute very loosely because that's an operator, right? Limit is an operator, it operates on something. So you're not really distributing it, but it works the same way. Let's tackle each of the three limits individually. And I think what we'll do is we'll also kind of review calc on it as well. So I'll actually break down every step. We're dealing with scalar multiple function, right? Remember what that law was? Right, you're taking the limit of a scalar times a function. How do you evaluate it? It's the scalar times the limit of the function. There were not two, there's what? I think 6 total laws that allow you to just do direct substitution. Yeah, I'm going to kind of break it down as a big deal. Well, this isn't a summary difference. This isn't a product. It's not a quotient. It's not a power. And it's not a radical. That only leaves one more. The composite function theorem. So you remember what that says. Taking the limit as t approaches a of f of t. As long as f of t is continuous at a, then that limit is f of the limit as t approaches a of a, or of t. Right? In other words, it's just f of a. Where's e of t continuous?
At t.
So t is not a set of values. It has to be continuous over some set, over an interval. So where is e to the t continuous? Just positive reals? All reals, right? Domain of the exponential function is everything. And functions are continuous over their entire domain. Which means it's continuous at 0. Which allows us to do that. What is the limit as t approaches 0 of t? This is one of the fundamental limits that was introduced in Calc 1. Limit as x approaches a of x is what?
X.
So limit as x approaches a of x equals what? It's just not a of x. It's just a. 2 ways you can prove that. Just look at the graph of x. It's just a straight line. You can also use the epsilon delta definition of the limit to prove it. Either way, that is a known limit that we use, which means this limit here is just 0, right? What's e to the 0?
1.
That one is 7.
Wait, sorry. Why is it 0 again? Because it's just t.
T's approaching 0.
Right.
Again, that is kind of like the breakdown that you do. Just go, let's just 2 e to the 0. Just so. Now this is a quotient. But the problem is, what's the limit of the denominator?
0.
Which means you can't do it. So that doesn't work. So you can't break it up that way. But isn't this form kind of one of those special forms? Let theta be negative t, you'll change the variable. As t approaches 0, so does theta. Well, now if you look, we have a scalar multiple, right? What's that limit?
1.
That's 1.
So why would theta not still be 0?
It is. But this is one of the special limits that was proven.
Sine of x over x.
Limit as x approaches 0, sine x over x. In Calc 1, that was proven to be 1. I think it used squeeze theorem to prove that. So the next limit then was up. Okay, why does PowerPoint stop working with the touch? That's getting annoying. That's power, right? And again, I'm going to break it down. Difference rule. What's the limit of a constant? Which makes that limit 1. 1 minus 0 squared, 1 squared, 1. There's your limit. 2, negative 1, 1. Again, very, very straightforward. And notice, there's nothing new there. Right? That was all Calc 1. We just did it 3 times because there were 3 components. I won't write out. That's not the right one. I won't write this step out this time. I'll just go right to evaluating the limits. But notice this is now a limit at infinity. First, does that limit exist? Does the limit as t approaches infinity of e to the negative 2t exist? Yes, what is it? If it was infinity, the limit wouldn't exist. It's zero. Or it's e to the minus infinity,
Oh.
Because it's a negative
right,
exponent.
pulling out the- Okay, so then you.
which is the same as 1 over. Yeah, that's just zero, right, for that reasoning. Again, you could do a change of variable. Let x be e to the 2t, which would require another change of variable. But the idea is, what does e to the 2t do as t goes to infinity? It just grows without bound, it's 1 over that, which means it shrinks to 0. What's that limit? How'd you get it?
Just take the highest power on the numerator and denominator, and that will be the limit.
Take the highest power,
No, the highest degree.
and what about the highest degree?
You divide it by the power of t. Or sorry, like you take the highest from the numerator and the highest from the denominator, and that will be your numerator.
Several arguments for that. First, you could just look at how the function behaves. As t gets really, really large, that plus 3 doesn't really matter. That minus 1 doesn't really matter. That, for a very large t, that function behaves as 2t over 3t, just 2/3. The second argument is the algebraic argument, where you factor out t from the denominator, and then that goes into the numerator 1 over t. You'll get 2 over 3. You could also use L'Hopital. Take the numerator derivative of the denominator.
If this is on like a test quiz, would you want us to show how, like, the steps we're doing to improve the limit, or just show?
Unless it asks you to. You could just evaluate the limit. What's that? Again, if you need to. First, do a change of variable.
Actually, no.
Pi over 2 times you get. It's not a good mathematical answer.
Like, just like we did,
Not necessarily. Because technically there is no largest number you can get.
I mean, like, within its domain, like, within.
Even within the, well, the domain is what? All real numbers, right?
Range.
And so, because of that, there is no largest.
Like, this is like the largest you could get in its range of.
Well, true, but why are you doing the largest that you can get?
Because it's.
Well, x is approaching infinity. Right, so that'd be like, you're conflating output and input. If that was the output, right, what value of x would make the inverse tangent infinite? That's kind of like what's the largest value you can get out of inverse tangent.
Yeah. That would be hilarious.
I was just gonna say, like, that's just where the bounds end on the tangent of this graph.
True. True. That doesn't necessarily mean the limit has to exist, though.
What?
Doesn't necessarily mean the limit has to exist.
Well, there's nothing stopping it.
That'd be like saying, what is the limit as x approaches infinity sine of x? By your reasoning, that'd be 1, which is not the limit. The limit does not exist. So it's a combination. Yes, first, the inverse tangent has a range minus pi over 2 pi over 2. Second, the inverse tangent is not periodic. So it doesn't oscillate. It's 1-to-1. Then you have to look at it, well, what's really being asked? So if you look at tangent of theta equals x, limit as theta approaches what angle between in the range of inverse tangent of tangent of theta gives you infinity. Well, there's only two ways you can get. Well, there's only one way you can get infinity out of the tangent, and that's when cosine is 0. Cosine is 0 in only 2 places: minus pi over 2 and pi over 2. But 0 minus pi over 2 means that sine is negative. So your tangent would be negative infinity. Leaves you pi over 2. Also, just look at the graph of the inverse tangent.
Wait, that's what I said?
You said something about largest value. No, that was you who said largest value.
Yeah, I said the graph, the bounds of it are 2.
Right, bounds are minus pi over 2 and pi over 2. What does that mean about as it approaches infinity? Because if, for instance, inverse tangent didn't have asymptotes, then it wouldn't be defined. Right? There would be no limit.
I guess that was kind of it's just that's like the height of
But again, when you're talking about the highest number from the graph, that is range. But what's that got to do with x approaching infinity?
Is it the image not be usable past and maybe pi over 2 and cause the image it's going to its pi over 2? It's like you can't determine anything once you get past pi over 2. So that's the only. It couldn't possibly be pi. It's tangent. Inverse tangent. So my thing is that it just couldn't be larger than pi over 2. That's that.
Are you looking at only the range there?
Yeah.
Now the limit doesn't exist. Because x equals infinity is not even in the domain. So you also have to look at the domain. The reason that your argument works is because the domain of inverse tangent is all real numbers. If the domain was, let's say, -1 to +1, that limit wouldn't exist because x can't go to infinity. X can only go to 1.
So you're saying.
And also,
So if it was a different limit, that larger.
even if we say that it's all real numbers, now as x goes to infinity, are you getting the largest value in the range? Yeah. So it has to be because of the way that the inverse tangent behaves. But you can't just say it's because it's its largest value, because that's not always true.
I suppose.
Because I don't want you to make that mistake, for instance, for a function that wouldn't be like that. You just give me the largest value, even though it shouldn't be.
Well, yeah. It's because of how it's behaved, and that's what value you can get because of.
Now turn that into a mathematical argument.
It's. I love magic. Not necessary.
Which is a shame because engineers make more than mathematicians.
Well,
So honestly,
correct.
it should be above your pay grade. Because if it wasn't, it'd be above mine. And that's a problem.
Petition whoever decides who gets paid things, paying the word. I don't disagree.
Just pay my union dues and say you can deal with it. I certainly don't make enough to deal with them. You could pay me enough to deal with them, to be honest. T approaches 4 now. Again, I'm going to skip that intermediate step. Yes, early. Tomorrow is primary election day, I believe.
Yeah.
In New Jersey. But early voting started last week, and I had nothing but taxes. What's that limit? What's that limit?
Zero.
What happens if you plug in 4?
Zero.
No, you get zero. Zero.
You get 0, 0.
You can
which is indeterminate. You could, as an easier way.
But he's not passive though. 0 0.
Non-asymptotic, it's removable.
Wait, so when? Oh.
He's
Could, again, as an easier way. That's actually harder than Motel. Isn't T minus 4 difference with 2 squares? Square root of T and 2. Doesn't T minus 4 then factor to root T plus 2 times root T minus 2? We're left with the limit as T approaches 4 of 1 over root T plus 4, or root T plus 2 rather. Supported. What is that limit?
Root 2 over 2.
Wrong trig function. Which is what? Which one? Direct substitution works because tangent's continuous at 4. Or, sorry, tangent of pi over t is continuous at 4. In fact, its only point of discontinuity would be at 0. There's your limit. Good. $225. Move on to the next topic.
Your names on them of like who lives there, and there's cameras in the hallway. So who are you putting that on for? like they're going to know it's you wearing it, bro. Like, come on. We were trying not to laugh because I was thinking it was a yo Kiki, and she's like,
Hey, no.
I was like, you go to Rowan University, you have no, like, there's no reason for you to be wearing that.
Who remembers the definition of the derivative?
The instantaneous.
That is interpretation. Of the definition.
No, you're talking about the norm of the.
What's the definition of a derivative?
Like
It's been a while.
Yeah, bro, we don't wanna.
It's like we got. Yeah, I'm not sure.
What's the definition of
Oh, that makes sense. That makes me sad.
I'm phoning friend, and friend is you.
That's a bold claim.
I'm phoning an acquaintance.
It's less of a bold claim.
F of x plus h minus f of x all over h. With the limit in front.
So, with the limit in front, be
Yeah.
more specific.
The limit as h goes to 0.
Yes.
Oh.
Limit as h approaches 0,
I do.
or you may sometimes see as delta x approaches 0, h and delta x are used interchangeably. F of x plus h minus f of x all over h. That is the definition, actually, that's the definition of derivative function, not necessarily a derivative.
Oh.
Right? Derivative itself is a scalar. Interpretation is slope of a tangent line or instantaneous rate of change. Well, what do we think the definition of the derivative of a vector is? It's the exact same thing. Provided the limit exists. But that's a limit, right? And isn't this itself, this entire expression, a vector? How do we take limits of a vector? What do you mean? How do you take a limit of a vector? How do you just do it? Yeah, how do we just do it?
But taking the limit of the individual components
So I think we're going to find the derivative of a vector.
by
Taking the.
Because it's just a limit. But what's, I will be getting there. What's the definition of an integral?
The opposite.
That's an antiderivative, not an integral.
One step further.
the area under the curve.
That's interpretation. What's the actual definition of an integral?
The antiderivative plus c.
Yeah, that's
Damn.
Would it surprise me? We can count one.
Yeah.
Which means you should know this.
Actually.
I think there's only 1% of us who actually teach the true definition of an integral in Cal 1. It's fallen out of favor, sadly.
I did not like my calculus.
Limit of the Riemann sum.
Yeah.
The limit? What?
Limit of the Riemann sum.
What's the limit?
Oh, damn.
It's a,
It's
it's a sum. It's so there's more than one Riemann sum. There's actually, in theory, an infinite number of Riemann sums for any given function.
Isn't it like all of the bits of the.
But I'm not going to get too into that here. Look up the Calculus Volume 1 for OpenStax, Chapter 5, maybe Section 5.2.
Is that also the one where it's like
It'll define what a Riemann sum is.
all positive real equals to a negative 1 well,
No, that has to do with infinite series. Yeah, that's just a weird result. That's more string theory, because that results in string theory. But we'll actually look at integrals later. All that to say, because you brought up infinite series, how do you evaluate infinite series? What's the definition of infinite series? It's the limit of the partial sums. So guess what you just spent all your time doing? Limits. That's what calculus is. It's just a limit. Properties. Properties still hold. You still have the scalar multiple law, sum difference law. Except now we have three types of products, right? We have scalar product, more like a scalar multiple product, scalar product, dot product, and cross product, which means we have three product rules, one for each of the three types. Henceforth, this is known as a scalar function, and that would be like a vector function. Right? So the scalar product is exactly what you think it is. The dot product rule is exactly what you think it is. Cross product rule is exactly what you think it would be. There's no quotient rule,
I'm confused with that.
because there's no such thing as quotient for vectors. You can't do a vector divided by a vector, it's not a defined operation. So you lost quotient rule. At least for vectors. There's a chain rule. Right, but you have to keep in mind when you're doing vectors, you can't do a vector function composite with a vector function.
So it has to be some vector and a function.
So it's a vector function composite with a scalar function. For now, when we get to multivariate, you can actually then composite a vector with a vector with the condition that the number of variables of the vector field dictates the maximum dimension of the vectors of the vector function. We'll get into that when we get to vector analysis. I will say I barely use these rules, because I'd rather just take the cross product first and then take the derivative, rather than do two cross products. That's just me. This is going to be used in theory. This one is useful. R dot R is a constant, then R dot R prime is 0. So if you dot a vector with itself and you get a constant value, then the tangent, because that's what our prime represents, right? A tangent, is actually normal. It's perpendicular to the original curve. No, that's what dot product is. Right? The perpendicular. Principal unit tangent vector, I already mentioned. Tangent vector is any vector that is tangent to the curve. One such example would be R prime. Well, we define a special type, the unit tangent or the principal unit tangent vector, which is just normalizing R prime. So find R prime, make it length 1. And that will be represented with a capital T. Integral. I'm not going to formally define it. Because dealing with Riemann sums with vector functions is just a pain in the ass. Instead, I'm just going to go over how we evaluate. Well, the antiderivative, fairly simple enough. It's an anti-derivative, so you just anti-differentiate each component. Taking an integral, because the integral is by definition a limit, the limit passes through to each component, so you just integrate each component. Again, there's nothing new here. This is again just calc 1 and calc 2. You just have to do it to each component. And of course, by definition, each of those functions is a real value function. And again, as I mentioned, we call these integrals. We actually mean the Riemann integral. There is another type of integral, the Lebesgue integral.
It's like the horizontal integral.
No, Lebesgue integral has to do with measure theory. You probably won't touch on it as an undergrad. I studied it in graduate real 2. It sucked. I will do it for this problem, but I won't do it for future problems. Thank you for that. Why are you- being weird? Just distribute the differential operator through each component. What is the derivative of 3 cosine of t? What about 3 sine of t? And 14. There's your derivative. Now let's see who's paying attention. What kind of shape is that? What kind of shape is R?
It's like purple. Cylinder.
It was in the worksheet.
No problem specific.
I don't remember, but it did mention it in the worksheet. This is a helix.
No, not for, yeah.
I think the problem, the worksheet was 2t, not 4t. It's a helix.
For some reason, I was assuming the sign.
Which is a spring shape.
Yeah. That's
What's that notation represent?
second derivative.
How do you find a second derivative?
Take the derivative of the first derivative.
R double prime. And again, I'll write this out. I'm not going to write it out the way I did last time. What's the derivative of that first component?
Negative 3 cosine t.
Derivative of the second component? Derivative of the third. There's a second derivative. Can we write this? Oh, sorry. No. What does the left-hand side give you? What's the left-hand side saying?
It's the magnitude
Of the first derivative.
What's the right-hand side?
Just for the vector of the first derivative. Or just
The vector component.
I agree it's the first derivative, but the first derivative of what?
The vector component.
or
What do you mean vector component?
Like the negative 3 sine t cosine t or
That's 3 components. So what do you mean when you say vector component?
With all the components.
Something specifically about components.
Because the left one says vector, that was just saying what the T component.
What does R represent? Just R, not the vector R. Remember that notation? What function?
Function of T.
It's the magnitude, right? Left-hand side is asking for the magnitude of the derivative. Right-hand side is the derivative of the magnitude.
Oh, so that would be
So you find the magnitude first and then take its derivative, which is usually hideous. However, I could write this. Because r prime is just velocity and the magnitude will give you speed. So that's fine, but we'll deal with that later. But we already found the derivative, right? So square root of the sum of the squares, what does that equal?
25 or 5?
That is just 5. That's nice. So when you're dealing with a helix, the tangent is always constant line. The length of the tangent vector doesn't depend on position, where you are on the helix. Which means going along that helix, you have constant speed. That doesn't necessarily mean you have constant velocity, though. It just says constant speed. We'll get more into that when we study motion in space, which is after the exam. Magnitude of the second derivative. Again, magnitude, square root, sum of the squares. That's just 3, isn't it? Nothing new. We're going to find u, derivative of u cross v first. Two ways. both methods. Remember, order of the cross product here matters now, right? And if we go back, the order that they appear doesn't change. The order of the sum doesn't matter, right? Just the order of the cross product that you take. And so that's the first way we can do it, is to actually use the product rule. What is, oh, I just did U prime, I just did U instead of U prime. Keep that up here for now. What's U prime? Okay.
Minus the UT squared.
Uh-oh. How would you do a cross product with three-dimensional or two-dimensional? It's very easy. If you're dealing with a vector in 2D, does not mean that your third dimensional component has to just be 0. That's how you do it. Now, what's the derivative of V?
Yeah.
And then we're just going to add a 0. Now we got to do each of those cross products. First component is 0 minus 3t squared cosine of t. Second component, negative 3t squared sine of t minus 0. Third component, negative 10t cosine of t minus sine of t. Now we got to do Second cross product. 0 minus negative t cubed sine of t. Negative t cubed cosine of t minus 0. Five t squared sine of t minus t cosine of t. So it was minus t sine. No. T cosine. Which means that should have been a sign there. Just make sure I get that right. Yeah, 5t squared sine t, and then that, yeah. Now I just have to write that as a single vector, right? What are we gonna have? Negative 11t cosine. Thank you for that. I'm gonna rewrite that. I'm also gonna move it down for space. 5t squared sine of t minus sine of t minus 11t cosine of t. Right? That's using the cross product rule. So we had to do two cross products there. Method 2. Take the cross product first. And so again, treat the v like it has that 0. First component should be t cubed cosine of t, right? Second component, negative t cubed sine of t. And the third component, I'm out of room. That's always lovely. Let's move it. Negative 5t squared cosine of t minus t sine of t, right? This should be negative here. They should all be negative. And everything else should be right. Now take the derivative. Let's take the derivative of the first component. So how would you do it? Don't tell me what the derivative is just yet.
So you go one by one.
First component. So yeah. So how would you do the derivative of the first component?
Oh, you have to do the, like, method one.
Product rule. Second times derivative of the first plus first times derivative of the second. Right? That second component is not also a product. That third component, first is going to be a sum rule, but each of the sum rules involves product. Oh joy. First term of the third component, right? Minus and then minus. Oh, but then look. Right, they combine. So I'm going to rewrite this. I'm going to erase it and rewrite it. And is that what we got from the first method? Better be, right? So you get to do whichever method you want. There is, again, two ways to do this. One is definitely preferable over the other. Is to use the dot product rule. Dot products. Is the dot product commutative? It is, right? Oops. What did we say E prime was?
10t 1 and then minus 3t squared.
Now take the dot product, what do you get? What is their dot product?
It has two u times.
Is dot product commutative? So A dot B is the same as B dot A?
Oh,
So those are actually the same term. How do you take dot product?
First term times the first term. And the second times the third term.
What do you do with them? So what is that dot product?
With the two.
No, ignore the two. Just the dot product of the two vectors.
oh, it's
50t
u.
Keep going.
t, and then
What about T?
t times t, right?
What are you doing with the T? It's 50T. What do you do? Hmm?
You're adding
Yeah. So you have to add the T.
Oh, sorry.
And then what's next? And I'm just writing it in descending order. That'd be your derivative, right? Second method. Take the dot product. But what happens when you take a vector and dot it itself? That's the cross product. Any vector cross itself would be 0. Take a vector, dot it with itself. It's not 0. If you take a vector and cross it with itself, it's 0. It was one of the properties. Vector dot with itself is the square of its magnitude. Its magnitude would be the square root of 25 t to the fourth plus t squared plus t to the sixth. So just square that. Oh, well, that's now a really simple function. Right? What is that derivative? And give it to me in descending order.
T with it. 100t cubed.
What about 100t cubed?
plus 100 t plus 2t.
Is that the same thing? Better be. This is definitely the preferred method here. Definitely a lot easier. But again, you could also just do dot product rule. And this is why I say in general I don't use the product rules. Even the scalar product rule, I tend to just distribute that scalar thing first. I'll do the operation first and then take the derivative. I'm more likely to use the scalar product rule than either of these two. Dot product or cross product rule. I'd much rather prefer to do the operation first and then take the derivative. And again, it boils down to, do I want to take the dot product twice or once? Do I want to take the cross product twice or once? I'd rather do it once. So show that u dot u prime is equal to u times u. I'm going to stick with 3 dimensions. Without loss of generality. Assume that u is in R3. And define it to be u1, u2, u3. Then what is its magnitude?
The square root of u1 squared plus u2 squared plus u3 squared.
Take its derivative. So this is general power rule, right? Times the derivative of the inside. What's the derivative of the inside?
Including the square root or no?
No, it's inside the square root.
2u1 2u3 plus 2u3.
What'd you forget?
Over to all that. Plus the constant.
That's with antiderivative. u1 squared is its derivative to u1.
u1 first power.
So it's just 2u1. What'd you forget?
Plus u2.
What'd you forget? Isn't u1 a function of t?
Yeah.
So you forgot chain rule?
Oh,
No.
I'm going to use the prime notation here to save time.
the house, you want,
Du over dt.
And it's implicitly stated that each component of u is a function of t, because u is a function of t. Oh. But when we actually do this, we're going to get this, right?
oh, and then could you multiply the denominator by the top together with the square root and then cancel out that?
I would. Well, u1, u2, u3, that forms u, right? What would u1 prime, u2 prime, u3 prime form?
Right.
Isn't the numerator u dot du? But we said that whole thing was just du dt, right? Multiply both sides by u. And you have your result. And I say without loss of generality because clearly, if you're in Rn, the work is exactly the same except you have n components instead of just 3. But the work is identical. So we didn't lose any kind of generality there. That's what it means when we say without loss of generality. The work is identical, just possibly more components, right? So we will finish up next time. I did hear it mentioned, yes, I did post the extra credit assignment for the first exam. That will be due on the day of the first exam. Right, so make sure you do it. And again, everything else is the same. So what I did decide to do for the exam is the charts and stuff I will print out and include with the exam, so you don't have to worry about printing them out.
That's like the integral formula.
Yeah,
and the-
those tables.
Okay.
And I'll do the quadrant,
Yeah, the surface area of
the quadrant surfaces as well. Format table print out and include with the first exam, so you don't have to worry about it.
Okay.
So,
We're getting on the formula sheet, basically.
so all you need to worry about is the reference sheet.
Yeah, the green sheet.
Oh, so
yeah.
all the stuff on the left is all good.
I'll print out
Okay,
the
okay.
tables and everything, I'll include with the exam. So you don't have to
I
worry
was
about it.
gonna say, could you look
I'm just gonna write down a couple of-
So just the
Right,
green
it's
reference
good.
sheet.
Oh,
Yeah,
yeah.
I'll include anything else.
Alright, perfect.
Yeah, just
See you on Wednesday.
What else?
See you on Tuesday.
Yeah, we can sell it.
Yeah.
That way, like, we can apply it.
Yeah.